And yesterday we heard a lot about the connections of this meeting with Stockholm in various ways, meeting and its participants. And I also have a connection to Stockholm with this meeting. It was in Stockholm where I saw Jim the first time during the photosynthesis meeting in 1989. Yeah, 89 I saw Jim. I'm absolutely sure he didn't see me. I was a tiny, not physically, but otherwise tiny PhD student. So I'm not sure, I cannot really say I met him there, but I saw him there. And he was at that time already one of the, let's say, gods of photosynthesis research. I had read or seen his books he had created at that time, this book series about photosynthesis, and I think this was also a major achievement.
I stopped doing that because when people introduce me to give a talk, they say, oh, he's well known for his book series. I thought, that is not what I want to be well known for.
Okay. But you were already well known for other reasons to me.
It's a very good book series. It's very effective.
Okay, so now I start really, and I think you all know what is shown here. About something like 2.5 billion years ago, some people say it's 3 billion years ago, it's actually disputed, oxygenic photosynthesis was invented. And this process has shaped the atmosphere, so essentially all oxygen from the atmosphere stems from this process. And I was just yesterday wondering how it is about cytochrome C oxidase. How much does it contribute to using up the oxygen? Do you know? I guess it's less than 100%. No, I mean today.
0.1% of the amount that's produced by photosynthesis.
Really? Only 0.1%?
Yeah, I did have a slide on it.
Uh-huh.
I decided not to show it.
Okay, so in that sense, photosynthesis is more powerful in affecting our atmosphere. And it also has affected our geosphere, because the oxygen in the atmosphere has caused withering of stones and so on. So our geology is strongly affected by the oxygen content of the atmosphere. And this always happens in Photosystem II. You all know that. And here, unfortunately, somehow the graphics are not so nice on the screen. But you all know that this is a structural model of Umina, and which has promoted the field a lot with other crystal structures. But one should also not forget that all this mass of protein would be essentially meaningless without all the biophysical studies telling us what is happening in Photosystem II. And in Photosystem II, we have a manganese complex, you all know very well. And this manganese complex is cycling through various oxidation states. And today it's essentially undisputed that these oxidation states are starting in the lowest oxidation state, a manganese 3,3,3,4 state, and going to the highest oxidation state, a manganese 4,4,4,4 state. And then an additional electron oxidizes either manganese or directly the substrate water. We have spent quite a lot of work in the past to show that there are further intermediate states that kinetically can be tracked. So, for example, I think we could show that in the S2, S3 transition, or we start with S3, S4, S0 transition, there's first a proton released and then an electron transfer is taking place. The same happens in the S2, S3 transition, and in the S0, S1 transition, it's the reversed order, meaning that first an electron transfer to an oxidized tyrosine takes place after a light flash, followed by a proton release, and all these steps are kinetically separated. Meaning that there are a lot of opportunities, for example, for time-resolved XFEL studies to look for these intermediate states. But we yesterday heard from Junko Jano that they saw only a very tiny difference if they looked for this transition here. And this presumably to some extent relates to the fact that in protein crystallography we cannot see protons. So these transitions may involve a movement or likely involve a movement of protons, and they in tendency stay invisible in protein crystallography unless you reach a resolution of about 1 angstrom, which is far away for Photosystem II. So therefore, we approached time-resolved infrared spectroscopy. And I will not discuss much details. It's just to give you a flavor. This is a signal measured with a quantum cascade laser, meaning at a single wavelength, but it's a tunable quantum cascade laser. And we can reach an excellent signal-to-noise ratio now. So you see here it's milli-OD scale, and it's 0.1, and we are on the order of, our signal-to-noise is on the order of 10 to the minus 6. So for the strong bands, like the QA minus band, we have reached single shot sensitivity, meaning we can measure with a single shot an infrared time course. For the weaker bands, we need to average, of course. What's important is, this is an example for the, it's not written here actually, for the S3, S0, or the different S-state transitions. And for the S3, S0 transition, for example, we see this millisecond phase here, clearly, but we see that's happening a lot before. So, and that's in general the case for all S-state transitions. We see that before the electron transfer, there are events happening, and this is a field to explore, and we will try to do so in the future. Another aspect of Photosystem II, another, I think, fascinating aspect is the self-assembly of the manganese complex, the so-called photoactivation process. And that's the, it's called photoactivation traditionally. In practical terms, it's an oxidative self-assembly. It means we oxidize the tyrosine Z by light, and this oxidizing power facilitates, promotes the assembly of a manganese complex. And this is a paper mostly done by Miao in the Zuni group. It leads, or was a paper on the structure of a manganese complex in the absence of manganese ions, as well as intermediate states of the assembly and the disassembly. You see here, there's intermediate states of the assembly and disassembly, and assembly. Resolution is pretty low, but one can see electron density somewhere around manganese, or in the middle of manganese 1 and manganese 2. And so we conclude that in these intermediate states, these two sites are occupied by manganese ions. And from earlier X-ray absorption spectroscopy studies, we know that in the assembly and in the disassembly process, we see a manganese-free dimer-oxobridge dimer of manganese ions. So we conclude that an intermediate state of a photosystem, we have manganese at manganese 1 and manganese 2 sites occupied with manganese-free ions bridged by connected by a dimer-oxobridge. Another interesting aspect of the study is the structure when the manganese ions are fully removed. And the surprising thing is that the ligands are essentially exactly at the same position without the manganese. I was really surprised because I thought, so if always these 4 manganese ions, if it's calcium ion, a big blob, and if there needs to be some empty space if you remove it, but there is no empty space. And if you think about it, it's very nicely visible for the manganese number 1. So the manganese number 1, it's sitting here, and if you remove it, the distance between these two carboxylate ligands and the histidine ligands, they remain unchanged. And this is understandable if you have a manganese number 1 here, and these ligands here, they're at a distance of 3 angstrom and 2.7 angstrom. And if you remove the manganese, they just become hydrogen bonds. So it's the hydrogen bonding distance between the neighboring ligands, and you remove the manganese, they become hydrogen bonds, and the distances can stay at the same, and the charge is also compensated by that. So it's an, I think, nice finding. I was surprised. Next step, water oxidizing manganese oxides. It has been noted, and it's nicely visible in this scheme, that the core of the manganese-calcium complex looks like an oxide. It's an oxide, inorganic oxide core bound to the protein on one side or some sides, and it has an more open sides where it's interconnected to water molecules. And this, of course, has motivated, this has motivated investigations on manganese oxides as a catalyst for water oxidation, synthetic manganese oxides. Philipp Kurz, who is now in Freiburg, was one of the pioneers in these studies, and he synthesized manganese oxide particles, aiming at a mineral which is called marokite, manganese calcium oxide particle. And it has this marokite has some structure motifs which are close to the protein structure, the crystal structure of Photosystem II. However, it turned out that they synthesized this compound, but the really crystalline compound of this marokite was not active in oxygen evolution. So the real marokite mineral was inactive, and we investigate by X-ray absorption spectroscopy the active form found in the course of this marokite synthesis. And this active form of a manganese oxide is a form of a birnessite. Birnessites are layered manganese oxides. So you have a diamoxobridged or edge-sharing octahedra of manganese ions layers, and in between you have in the birnessites a water layer with cations embedded. We see that these active oxides are kind of very well disordered manganese oxides, which may have some indications that they also contain this distorted cube structure, manganese calcium structure, if it's a manganese calcium oxide. Evelina Tsareva in Berlin, she developed electrodeposited manganese oxides. And one interesting aspect is that depending on the electrodeposition protocol, you get different structures and different activities. If you do an electrodeposition with a constant potential, a constant current, you get a manganese oxide which is essentially inactive. It's a birnessite which is well ordered. You see it with Ixos peaks, so longer matter-matter distances. It's a well-ordered birnessite, but it's catalytically inactive, as you see in the CV. If she uses a different protocol, it becomes catalytically active. If you use a voltage cycling protocol for electrodeposition, we get a catalytically active, so this is the inactive oxide. There's no CV wave for catalytic activity. This is the active oxide, you get an active oxide. It's again of a basic birnessite type, but much more disordered. You don't have these long distance peaks here, and you get additional structural motifs. And in addition to edge-sharing octahedra, you get corner-sharing octahedra and more diverse structures. We compared these different oxides to the Photosystem II. In Photosystem II, we can change the oxidation state by application of light flashes. And that's shown here in the first row of Photosystem II. If we apply light flashes, if we go through the S-state cycle, the oxidation state changes from 3.25 to 4.0 of the manganese ions coupled to structural changes. Changes which most likely involve also bridging oxygens. In the catalytically active and inactive oxide, we can do the same by application of electric potentials. So they also go from, in this case, from oxidation state 3.4 to 3.9 if we change the applied electric potential in a certain range, which is again coupled to some changes in these, moderate structural changes, especially in the catalytically active oxides. And the catalytically inactive oxides with structural changes are very limited. And the inactive and active oxides, they both are able to undergo oxidation state changes. And even the difference is that in the active oxides and also in the catalytically active manganese calcium oxide, we reach, even at the highest applied potentials, we do not reach the all manganese 4 state. So we still have some manganese free ions present, and we figure that this is required to maintain a certain degree of structural disorder that helps us to promote formation of the catalytically active sites. There are other differences. Also, the rate of oxidation state changes is different in the catalytically active and inactive manganese oxide. So it's almost 100 times faster in the active oxide than in the active oxide. It means the catalytically active oxides, they both change their oxidation state if they change the applied voltage. But in time-resolved X-ray spectroscopy experiments, we see that this is a process which is much faster in the active oxides than in the inactive oxides. This is in line with impedance spectroscopy, something you cannot do on Photosystem II, but you can do on these oxides. And we see here also that it's roughly 100 times faster oxidation state changes in the active oxides. So the kinetics matter. This confirms this. It's done looking for absorption changes of these oxides. I just want to remind you that there are broad spectra of these oxides. With a shoulder here, we will need that later. Now I come to the last part, perhaps in a way the main part of my talk. It is about light-driven manganese oxides formation by Photosystem II. And a hypothesis how this might relate to evolution. Just to remind you, that's the Photosystem II containing a manganese complex. That's the Photosystem II not containing a manganese complex. There's not much of a void, not much of empty space in the crystal structure. Now we investigated Photosystem II from spinach, where we removed the manganese complex completely by a relatively harsh treatment, which also leads to a loss of the extrinsic polypeptides. Standard procedure in a way, and where this might be different. I'm pretty sure it is different actually. Then we approach some kinds of photo-oxidation of manganese ions. As opposed to a standard photoactivation protocol, we are using comparably high concentrations of manganese and comparably or very high light intensities, saturating light intensities. So what we observe or we look as an assay for the reduction of an electron acceptor, DC-PIP, which changes from a pronouncedly blue to a colorless form once it accepts electrons at the acceptor side of Photosystem II. If we have no manganese ions added and we switch on the light, we essentially see nothing or almost nothing in terms of oxidation of the DC-PIP at the acceptor side. For low concentrations, low micromolar concentrations of manganese, we see rapid formation of some activity which we do not completely understand. I guess it's some alternative activity, perhaps peroxide formation or some other oxidizing activity of the Photosystem II. It's not shown here, but just for comparison, if we have the active manganese complex, or photosystem with an active manganese complex, it's like that. And if we add now higher concentrations of manganese oxides, we observe a rapid phase of electron transfer towards the acceptor side, which then stops. And so it seems to compete with this slow oxidizing process. So here we have a strong, pronounced manganese concentration dependence of this rapid phase, which then stops. And we looked with absorption spectroscopy for this rapid phase in more detail. And one important point in double difference spectra, you see some indications, it's that green line, weak green line, some indications for manganese oxide formation of manganese oxides particles, presumably. And you may remember this resembles, vaguely at least, the manganese oxide spectra I showed you before. But this is not extremely convincing because these are broad spectra and not necessarily fully characteristic of manganese oxides. So we first assessed the amount of manganese ions associated with Photosystem II after a centrifugation step, and we find that as anticipated in the intact Photosystem II, it's 4 manganese ions per Photosystem II. In the manganese depleted Photosystem II, it's 0 within the accuracy limit of the method. And if we do these kind of illumination experiments, we get something like 65 manganese ions for photosystem II. So we have these 65 manganese ions per photosystem II, and now we investigated these manganese ions by X-ray absorption spectroscopy, and we see it's a relatively high valent manganese oxide. The oxidation state is 3.5. You see its spectra differ from the photosystem II spectrum. It's more ordered, and that we see very clearly in the XF spectra, where we have an ordered birnasite formed. So it's a perfect birnasite or bouzerite. These are two minerals which cannot be distinguished by X-ray absorption spectroscopy. They differ in the amount of water layers between oxide layers. So we have an ordered birnasite formed. The similarity to photosystem II is moderate only because we have these extended oxide layers formed. So these oxides, this is a structure, another structure picture of a birnasite structure, roughly the size of the oxide particles we may have formed. So you have these layered manganese oxides, you have cations in between. These cations also may be manganese ions, actually. Maybe also calcium ions. In our situation, we don't have a lot of calcium present, so I would rather think it could be other ions, cations. But we have some calcium present, we don't know yet. And so this is a side view and a top view on these structures. So you can see that these cations might form some cubane-like structures. And that's in a way the central result. We think that we have a manganese oxide nanoparticle formed at the photosystem II. So it's most likely part of a photosystem II because it's closely associated with photosystem II because it sediments and centrifugation together with the photosystem II. And this leads us to an evolutionary hypothesis. And the relation, or the obvious structural relation between the manganese oxides on one hand and the photosystem II manganese complex on the other hand has given rise to hypotheses on this evolution. And there had been the hypothesis by Ken Sauer and Vitul Chandra, published in PNAS a while ago. And they said, okay, it may be that a photosystem acquired a manganese oxide particle. I think this is a nice idea, but not a very reasonable idea, because at early stage in evolution, you shouldn't have any manganese oxides around, simply. So we, in a way, turned this hypothesis upside down. So our working hypothesis is the following. We start with an anoxygenic photosystem. And this anoxygenic photosystem acquired the ability to oxidize manganese. And this is seemingly not very difficult. You just need to provide an oxidizing potential when you can oxidize manganese ions, as we do in the electrodeposition process, for example. When you form manganese oxide particles, and in the early stage of evolution, this may have been an important aspect that dissolved manganese oxides was oxidized by the photosystem, was used as a source of electrons for photosynthesis. And these manganese oxide particles formed at photosystem II at an early stage, the hypothesis is they were released from the photosystem, and part of these manganese oxides became manganese oxide deposits. So there's a paper from Johnson et al., from a Caltech group, and they indeed say that find evidence that there are early manganese oxide deposits in South Africa. I think on the Kalahari Desert, they found some evidence before the evolution of photosynthesis. And they concluded that there might have been a photosynthetic organism that worked as a manganese oxidizer. And now we show, in a way, that even today's photosystem, under some circumstances, which are not necessarily which are non-physiological, but under some circumstances, has the ability to form manganese oxide nanoparticles. And later in evolution, that's the hypothesis, with manganese oxide nanoparticles, they were kind of shrinking and optimized to become oxidizers of water, to become a water oxidizing complex, perhaps in an early stage an inefficient one. In an early stage we may have both mechanisms operating simultaneously, and to later it was really optimized to a perfect coordination sphere for the functional manganese oxide complex we have today in photosynthesis. And at this point I would like to thank my co-workers in Berlin. This work was actually done or headed by Petko Chernev and done by two undergraduate students from more kind of an extended lab course. Petko Chernev was involved, Michael Haumann was involved in writing up with still unpublished results, and Evelina Zaharieva, it's her specialty in a way to investigate synthetic manganese oxides for water oxidation. And at this point, I would like to thank you for your attention.
Thanks very much, Holger, for really interesting and provocative. Going back in some of the early work on photoactivation was done by Georges Chenet, and he had observed, and that was probably back in the 70s, that you could photooxidize a very large excess of manganese, and he called it sticky manganese because it would coordinate somehow to Photosystem II and prevent the successful assembly of the manganese cluster.
I think that's nine.
And then he found that if you could treat it with reducing conditions, you could wash it off and then retry and get it to assemble again.
Yeah. Perhaps you can send me the paper.
Yeah.
Rob also was telling me about it, but I could not find the paper.
Yeah, we also observed some of the similar kind of behavior when Anne Frances Miller in my lab was doing some studies in the 1980s. So I think that there's a prior work that really supports this, but at that time it was thought to be a side reaction. It's a really interesting idea that actually could be a reflection of sort of the evolutionary pathway. That's really very interesting. So let's open it up for questions. Let's Jim give the first shot.
There's a wonderful article called Mighty Manganese. It was written by Jeff Schatz. I don't know if you ever read it. But he made the point that manganese could have, I think, about 12 different valency states. And do you have any evidence that you can go to higher oxidation states? Okay, we could talk about manganese 5, but can we go to manganese 7, for example, or to a much higher oxidizing potential than?
No, we have no evidence of that. Of course, there exists potassium permanganate. The permanganate ion is manganese 7, but it's a pretty unstable ion. It tends to involve oxygen. So, for example,
if it's involved in, if it is involved in, say, OO bond formation, and it's unstable, that's okay because the whole process is so fast. But in our studies, we did never see any indications for oxidation state higher than 4.
Yeah, about the manganese 7, I'm going to present this after break. So with our 1 hour. But my question is related to the activity of manganese oxide. So very often, if you have older manganese oxide, it's low activity.
Yeah,
you have disorder, it's a high activity.
Right.
Have you think about this? What does the nature of activity come from?
Of course, we have thought about it a lot. So we actually think that it's a bit unfortunate that we cannot say more, but we think that you need this disordering to favor an active site structure that promotes oxygen evolution.
What is the nature of disorder?
Okay, no, this is that's the point. We don't know that actually. So this is a scheme from a paper in ES where we depicted possible structural motifs, and the XFS data it's really complex and it's in line with a lot of structural motifs. We cannot even it's not excluded that we have a similar structure when in Photosystem II. Being part of it, but at present, unfortunately, I don't see any good way to show which one is the active structure, site structure. Yeah, that's right.
I have a question about the data you showed about the structure of the dimanganese cluster early in assembly. And I'm reminded about some work way back with Bruce about the high affinity manganese binding site and the role of aspartate 170 in that. And that's not one of the ligands to that cluster. So I was just wondering whether you thought there was a prior oxidation at a different location and then movement into that pocket.
Right. I think we think like that. So, but it's not shown by this data, but based on this aspartate 170 data, we think that indeed the high affinity site might be here, which is actually a nice, one could nicely imagine. So this is the manganese 4 site, aspartate 170, and glutamate 333. And so the manganese 4 is kind of bound between these two sites, and this is indeed a good, intuitively would say it's a good site for manganese 2 to bind also. And now we assume that once it has bound here, this is not an intermediate we see in the data, and then it's oxidized and moving to one of these sites, manganese 1 or manganese 2.
You know, it's interesting bringing up that work. You know, one of the conclusions that Bruce Steiner made was that the ligands were pre-organized because the kinetics were very fast.
Yeah.
And so it's consistent now with the new structure that's coming out. I think it's really some nice consistency with the results.
Do you have any rationale on why the structure is, when the manganese is off, the ligands stay in the same positions?
Okay. Yeah, I think we know that only for the crystal. And the manganese depletion was done inside of the crystal. So they were oxidized by hydroxylamine inside of the crystal. And indeed, there are some indications that this does not happen if you don't have a crystal. So an attempt to do the depletion outside of the crystal, there was a tendency to lose extrinsic polypeptides.
Yeah, but I think coming back to Bruce Steiner's results, those were not done in crystals, and they were evidence of pre-organization. So I don't know that the crystal environment is really necessarily changing the picture very much.
Very nice. I'm very interested with the proton release. You said that every proton take out always with proton release. Can you demonstrate the structure with proton release or without proton release? It's possible to detect by example?
No, well, we don't know we don't know a lot about the protons, where they are coming from. And this is indeed the goal of these time-resolved infrared spectroscopy experiments, to learn more about it. However, I need to say it's extremely difficult. So technically these experiments are difficult. So it took us many years for the step scan experiment. I did not show. It took us 10 years to establish this experiment without any publication so far. And so it's really a lot of work. But aside from the technical problem, and now the assignment problem, the understanding, I guess it will take also 10 years, something like that, because we have no, as opposed to protein crystallography, we have no check what band in the vibrational spectrum corresponds to which carboxylate group. And we need to work out these tags by mutational studies and so on. So this is really tough work as well.
Maybe our artificial model can handle with this. Because I will present some result, the charge effect on the structure of the magnet, but we don't have the structure, we don't have the exact data. So.
Okay, let's thank Holger again for a really interesting talk.